Okay, so we will continue our lectures of chapter 14. So today is the third lecture, so basically this is lecture 10. We'll talk about partial derivatives. So just recall quickly, we are talking now about functions of several variables, even though we mostly will focus on functions of two variables in this section. But so let's just see, we have a function f of x, y in two variables, okay, which is defined in some domain D. And we have a point in this domain, so the point AB in the domain D. And the partial derivative of f at this point with respect to x is given this way. So it is actually this limit of f of a plus h, b, minus f of ab over h, where h is this increment that goes to 0. Okay? The partial of f with respect to y is given similarly, but now the increment happens in the y-coordinate, so we have f of a comma b plus h minus f of ab over h. H goes to 0. So the limit of this, okay? So this is very similar to, well, it's exactly the same as the derivative in one variable, and here we consider the variable x. That's why the increment happens in that variable, and the variable y here is considered just a constant, doesn't change. And here the variable is considered in y, and x is just a constant. So we denote this symbol this way for partials. We call it the partial of f with respect to y, the partial of f with respect to x. And since it is the same definition as in calculus 1, but with a variable x or y, to find such partials, it's actually very easy. All you have to do is differentiate with respect to that variable. So let's just look at this function here, x squared y plus y cubed. If I want to find the partial of this with respect to x, here is what you do. I mean, you just take this, consider x to be the variable, and y just a constant, and then the derivative will be 2xy plus, well, the derivative of y cubed, that is 0 because y is a constant. However, if you differentiate this with respect to y, then the derivative will be of the first one, so this term here, the derivative of that will be x squared because y, the derivative of y is 1, and here the derivative of this will be 3y squared because now that is the variable. So this is the partial with respect to y, okay? Anyway, so we can do a lot of examples like this, and pretty much all of them are, not so difficult as long as you know how to differentiate from calculus 1. I would like to talk a little bit about what these things actually mean, and I'll come back to this lecture one more time, but let's just see what it means. So here, when I was talking about the partial with respect to x, what you're doing, you're letting the variable x move, okay, but y is considered a constant. So when y is considered a constant, that means that corresponds to a cross-section of the surface that we have along the y-axis. And actually the derivative of that partial is the slope of that tangent. See that tangent along that cross-section? The slope of that tangent, because now when y is a constant, that is considered, the whole thing is considered as a function in x. And therefore, the slope of that function in x is really what the derivative is. Similarly, when you consider now x, so if you consider here x in this picture, x to be a constant, what you're doing really, you are actually taking the cross-section parallel to the y-axis, because now y is moving, right? X is a constant, and that cross-section intersects that surface on a curve, on a plane. That plane intersect on a curve, and so that curve, if you consider that curve at a given point, has a slope, and that slope, right, that slope is really what you're finding. All right, so let's just continue. So here is this example. The next example, I want you to look at it yourself, but this is easy again. Finding for this particular function, finding the partial with respect to x and with respect to y. Look, since these things are actually derivatives, and so the partial derivative of a function in x and y is still a function in x and y, it does make sense to actually wonder what happens if I take partials of that partial. And yes, we do. And so we call them second and third and so on ordered partial derivatives. Here is some kind of notation that it's kind of important to remember. So we will use this partial square f over partial x squared to denote the partial of the partial with respect to x both times, right? If you take the partial with respect to x and then you take again the partial with respect to x, this is the notation that we will use, okay? However, if we do that now with the other variables, so first I take it with respect to x and then with respect to y, we will use this thing. So partial square f and here partial y partial x. Okay, so the one from the right is done in the denominator. Here the one from the right is done first. So x is derived first and then y. Okay, and similarly you can do that. Okay, so here is, for example, an easy example where this is the function, and I say now find the derivatives, partial derivatives of higher order here with respect to x, x squared, and xy, and yx, and so on. Here is maybe one thing that will come up all the time. So when you actually take the derivative with respect to x and then with y, or if you take it with respect to y and then x, we have this, what we call it, this mixed partials, okay? And in this example that I did before, we found out that it didn't matter really. If you look at here, if you look at this example here, you see partial, second partial with respect to x and y, and second partial with respect to x and y, yes. And so it didn't really, so here is what you get here. And I don't know if I finished this, the other one. I didn't maybe. But you will see that it doesn't, I'm sorry, no, here it is. Yeah, well, I didn't finish it. Yeah, here is what you get here, and in both sides it didn't matter. So most of the time you'll notice that it doesn't matter. The result is the same if you take the partials with respect to x first and then y, or different order than first y and then x. So the question is, for what kind of functions is this true? And this is the so-called Clairaut's theorem, and it says the following. So if you have a function which is defined in some kind of a disk, and you are at a point inside that disk, then as long as these second partials are continuous, then they are actually the same. It doesn't matter on the order. So if you evaluate it at that point, remember, as long as they are continuous, if you evaluate them at that point, basically you get the same value, doesn't matter of the order of the differentiation. Alright, so there are some other ways to denote these partials, and we will use them later on when we talk about second derivative tests and things like that. So for example, this is partial with respect to x, is denoted sometimes that way, and double x this way, and so on. Okay, so I want you to look at this. The following is actually a nice construction that is used later on. For example, if you have a partial with respect to, a function with respect to two variables, then what happens is you put all these partials that you get in a nice matrix. And for example, you would put here partial of f with respect to x, and here partial of f partial of f with respect to y, and then here partial of f with respect to x squared and y squared and so on. Okay, so we'll come back to that again. So this is called, in general, for an n variable function, this is called the Jacobian of the function, and it's quite used in later topics. Okay, but here is the main thing here. Okay, when we differentiate it in calculus 1, we use the chain rule all over the place, over and over again. To find the derivative of sine x squared, we use the chain rule. We almost never use the definition of the derivative going through the limits. Now, well, I mean, of course, functions with many variables can be composite functions as well. So is there some kind of a chain rule for this type of functions? And yeah, the answer is yes. And here is how it goes. So if I have a function in two variables, and let's say each one of them is given as some kind of a function in t, right? Okay, then in order to find the derivative of this function with respect to t, here is how the chain rule will work. So the partial of z with respect to x times the partial of x with respect to t. But since x is a function in one variable, we are using dx dt, because that's a derivative from calc 1, right? And then the partial of f with respect to y, and the dy dt. Okay? If you have a function now in three variables, you can write this. It gets a little bit more complicated, but you can still kind of write this, okay? And so on. These things look bad, but they're not as bad. So I have here a function now in three variables when each one of them is in variable t, and here only if one of them is in two variables, so x is in s and t, and so on. They look bad, but they're not bad, okay? So look at this. This example is z is a function in x and y, and each one of them is a function in s and t, okay? Now to actually find the derivative, the partial with respect to s, here is what you do. You start here and you follow these roots, basically, these edges, basically, which take you at the very bottom to the variable s, okay? So in this case, we would be, for example, here, okay? So partial s, so look at the second part of this theorem. Partial s is given by partial of z with respect to x, and then times partial of x with respect to s. So here, from z we go to x, from x we go to s, right? So you multiply these edges when they go down the tree, and then you add different branches of the tree. So then it's plus, and then there is this part of the other path of the tree. So partial z with respect to y, partial y with respect to z, which is basically the right half of the tree there. And here there are some illustrations of this when the function has two or more variables, okay? So all you have to do is just follow these branches, and that's it. So this will conclude really this section. This is very short, and it's basically just how to find partials. And in the next section, in the next lecture, we will see how we can use this to study the function and understand the graph of the function and the maximums and minimums of these surfaces and other things we talked about today in class. So I'm going to stop here. Thank you.